Hello everyone and welcome. In today's video, I'm going to show you how to solve this problem. This is a problem on the conservation of linear momentum. So a larger fish swims toward and swallows a smaller fish at rest. If the larger fish has mass of 4 kilograms and swims 1 meter per second towards the 1 kilogram fish, what is the velocity of the larger fish immediately after the lunge? And in this problem, we are going to ignore the effect of water resistance. Let's look at the solution. So this is a problem on the conservation of linear momentum. And if we say momentum, it is nothing but the product of the mass and velocity of an object. In this problem, we have two fish, with the larger fish swimming toward the smaller fish and then swallows the smaller fish. So let's take the data given to us in this problem. First, we are given that the mass of the larger fish, M1, is 4 kilograms. And then it was swimming with a speed of 1 meter per second. That is before the interaction. Also, for the smaller fish, we know the mass as M2, 1 kilogram. And then it was at rest before the interaction. So V2 initial is equal to 0. It's 0 because this fish is at rest. All right, now this is all the information we are given, together with the fact that we are to neglect the effect of water resistance. So we need to go back to the definition for momentum. So momentum, which is a quantity given as P, is equal to the mass of that object times its velocity. So the velocity being a vector quantity and multiplied by the mass of the object, which is a scalar quantity, makes momentum a vector quantity, meaning momentum of an object is going to have both magnitude and direction. So the SI unit for momentum is nothing but kilograms, and then that for velocity is meters per second. So that is the SI unit for momentum. However, the law of conservation of linear momentum says that provided there is no external forces acting on a system of interacting bodies or a system of colliding objects, then the momentum before and after collision or interaction must be the same. All right, so that law, we can write it mathematically as the sum of the momenta before collision, which is initial, has to be equal to the sum of momenta after collision, so final. And this is the law that we are going to apply to solve this problem involving the two fish. Even though they are not colliding, they are interacting. Okay, so that is why in the definition I did mention it could be interaction or collision. We now have the mass of the larger fish, we have the velocity of the larger fish, we have the mass of the smaller fish, and we have the velocity of the smaller fish. So that is before they collided. And then after collision, what happens? Did they stick together? Did they move individually with their separate velocities? That is one thing we need to check. So if a larger fish swallows a smaller fish, what happens? The masses add up, right? So it would be the mass of the larger fish plus the mass of the smaller fish. And this we can call it as inelastic interaction. In terms of collision, we say inelastic collision. All right. So the law of conservation of momentum says that for this kind of interaction where a larger fish swallows a smaller fish, provided there's no external forces acting on this system. If I say system here, I mean the larger fish and the smaller fish. All right. Immediately after the larger fish swallows the smaller fish, we can apply the law of conservation of momentum to equate the total momentum of these fish before and after collision or before and after interaction. So we have the sum of momentum before collision must be equal to the sum of momentum after collision. So before collision or before the interaction, I'll refer to that as initial, and then after the interaction, I will refer to that as final. So the sum of the individual momenta must be equal to the sum of their individual momenta final. All right. So we can write for each of these fish the momentum before the swallowing or before the interaction, and then in the same sense, after the interaction, they stick together, they now become as a unit, and immediately after the swallow, the larger fish is going to have a particular speed, which is common to the swallowed fish as well. All right, so let's do that. So for M1, for mass 1, that is the larger fish, the momentum before the swallowing occurred would be M1 V1 initial, and then for the smaller fish, it's going to be M2 V2 initial. So this is the sum of the momentum before the interaction, and then after the interaction, we just saw that they are going to be one unit, right? Because a larger fish swallowed a smaller fish, so the masses are going to add up. So we can have M1 plus M2, and then immediately after the swallowing, the larger fish is going to move with the smaller fish inside it, so they have a common velocity. So let's represent that as V. So this, we can expand that like that to have their individual momenta. We can expand that. All right, so that is going to be M1 times that common velocity immediately after the swallowing. Okay, and also we can expand this, so that is also going to be M2 times that same velocity, because now they are as a unit. So we can factorize the V out, so that is why we have this expression here. Now the goal is to find V. All right, we have to find the velocity of the larger fish immediately after swallowing. All right, so to isolate V, we need to divide both sides of the equation by M1 plus M2. Since we've done this to the right hand side to retain the equality of this equation, so we divide by M1 plus M2. Here we can see M1 plus M2 on the right hand side will cancel out to 1. So 1 times V is just nothing but V. So the equation is going to be V is equal to M1 V1 initial plus M2 V2 initial divided by M1 plus M2. So now we can plug in the values, and then we can determine the speed or the velocity of the larger fish just immediately after swallowing the smaller fish. All right, so to find that, we have V is going to be, what is M1? We have 4 kilograms. So 4 kilograms multiplying V1 initial, which is 1 meter per second. And then we have plus the second fish, which is the smaller fish. So we have M2, which is 1 kilogram multiplying V2I. That is the initial speed of the smaller fish before being swallowed. So in that case, we were told from the problem it was at rest. So that means the speed V2I is 0. So we just multiply by 0 here, and then we divide by the total mass of these two fish. So M1 is 4 kilograms plus M2 is 1 kilogram. So now we can have velocity to be equal to, so 4 kilogram times 1 meter per second is going to give us 4 kilogram meter per second plus 1 kilogram times 0, so that is 0, so plus 0, so it will be 4 kilogram meter per second plus 0, which is the same 4 kilogram meter per second, and then we can divide by 4 kilogram plus 1 kilogram, so that is going to give us 5 kilograms. Now we can see that we can cancel out some of the units to 1, so kilogram here cancels the kilogram here to 1, and then we are left with the unit for speed, which is meters per second, which is the same as the unit for velocity, right? So our final velocity is going to be 4 divided by 5, which is 0.8 meters per second. All right, and this would be the velocity of the larger fish immediately after swallowing the smaller fish. All right, this is a good problem to give you a practice on the conservation of momentum when it comes to inelastic collisions. We need to understand that for inelastic collisions or interactions, after the interaction, the two objects stick together and then move with a common velocity. Just as in this case, a larger fish approaches a smaller fish at rest and then swallows the smaller fish. So now they are together as a unit. Immediately after the swallowing, we have calculated the velocity and we can see the mass added up, so the speed reduces. Okay, the speed for the larger fish went from initially what was 1 meter per second to now 0.8 meters per second. What a lunch, right? So this is just a fun problem for us to practice the conservation of linear momentum, and this brings us to the end of this video. Until then, I'll see you in the next one. Bye bye.